and welcome to this webinar. Where do the acceptance criteria and method validation come from? I'll give you some information on the webinar before we start. As you can see, I have enabled my webcam. I'm not suggesting that you need to enable yours, and I have muted the microphone for attendees because we have quite a lot of people on here today. Normally when we're running these training courses we do use both, so we'd have microphones and webcams the whole time. As this is being run as a webinar, we're going to leave questions to the end. So we will try and cover whatever questions you want to ask, and if you have questions afterwards you're welcome to contact me. But again, during the normal routine of doing a live training we would try and do this as we go through. And if you think of any questions as we're going through the presentation, please feel free to just type them into the public chat box. You might be able to see it there on your left of the screen at the bottom, and you could type in questions, and what I'll do at the end is review and see what came up. Okay, so you might think, oh, I'll forget that, I'll put it in now. Okay, so this is me. My name is Oona McPolin. I have met some of you before. We have lots of attendees from previous training courses. And my business is called Mourne Training Services. So you can see it's very focused on training. This business has been running for about 13 years now, and I primarily focus on training courses to do with pharmaceutical analysis, because that is the area that I have worked in for the last 25 years, say, in a GMP type of environment, but sometimes in development too. To give you a bit more background about what I do, well, we've got training courses, and I think a lot of you have got some information on those now, and that's what this webinar is an example of. But my hope that obviously the webinar is marketing, but my hope is also that it will be genuinely useful, that it is a mini training course, and there's a certificate, if you like, at the end to say that you have attended it. Other things, I do audits, I do consultancy, so I might mention that from time to time when I'm giving you advice on what I've seen. I visit a lot of companies to try and help them with a variety of problems, not just validation, also I do specification and technical things like HPLC. Previous to doing this business, I worked in a company called AstraZeneca, before that in smaller companies that you probably won't have heard of, here in Ireland where I am based. And if you're wondering, that is the accent you're hearing, is an Irish accent. And I am used to talking quite slowly when I do training courses, because I often have people where English is not their first language. So I'm hoping that you can understand me and you don't have any issues. So who's in our attendee list today? Well, we have quite a selection of countries. So I think for some of you this could be quite unsocial hours. So thank you very much for joining us. We have some previous attendees on our training courses, which is lovely. And I think there's a few people there who might be or who are already booked to come on a training course at the end of the month. So it's lovely to talk to you, and this will give you a little bit of an idea of how that will work, although it's a little bit less interactive today than normally. So just to get an idea of what sort of experience, what you're trying to get out of this, I have a couple of very simple questions for you. So the first one is this, just to see, are you currently involved in writing protocols? So just trying to get an idea. So just type in yes or no and we'll get an idea of what sort of audience we have here today. So I'll just give that a moment while it's building up, and we can see that, we can see that it's definitely most of you are. So we've got a few more, it's still going, so I'll just give it a moment. Okay, I think it's slowed down now. We've just got one more out of all done. There we go. So 78% are actually actively writing protocols, and that makes sense. That's why you'd want to come on a webinar like this. And out of those, the next question I have for you is just simply, do you actually need to do this then? Are you in the position where you have to individually go and think about these acceptance criteria? So again, we're getting very high numbers. Yep, we've got almost everybody is in yes. So no surprise, that's kind of what we're expecting, isn't it? That's why you're on this course, but it gives me a very good guide on what to focus on. So let's look at the question that I set as the title of the webinar. Where do they come from? Where are these acceptance criteria coming from? And I thought a good place to start was just to think about, well, what are acceptance criteria? And that can focus on where we need to go. So we're talking about some sort of measure that allows us to compare what we expect to happen and we consider to be okay with actual results. So very often we want numbers, but sometimes these are qualitative acceptance criteria. And our assumption is that if these results fit the expectations, our method in this case is satisfactory. Okay, so that's where we're coming from. And ultimately, what you've got then is a minimum standard. So it's not so much a case of how good is my method being your question when you enter into method validation. It's possibly more a case of how bad am I going to allow this method to be? Because that's what we're going to set. So this is the very worst I will allow this method to be. That's my acceptance criteria. So it's quite a good way to think about it, because you're not looking for perfection in methods, and we'll talk in a moment about why that's not possible. So what you need to decide is, well, how much am I going to allow it to go away from perfection? So those acceptance criteria will be required for what we call method performance characteristics, these MPCs. And if you follow ICHQ2, I think most of my audience today are from a pharma background, then in that document they're called validation characteristics. So these are familiar. You're all, pretty much everybody is involved in writing validation protocols at the moment. So specificity, accuracy, precision, and so on. So these are the things we have to set criteria for. Now in this webinar I'm going to focus much more on the quantitative attributes rather than the qualitative ones, just because of time. But general recommendations that I have for you on any acceptance criteria would be these two key things. The first one is that you have a clear link between the experiments you design and the acceptance criteria that you set. That sounds really obvious, doesn't it? But I review a lot of validation protocols, and very, very often there are things in there that just don't make sense. There is no clear link, or there's experiments that are being done, but there is no acceptance criteria associated with them. And then you say, but why are you doing that? And the answer is, not really sure. I don't really know. So that's number one. The second one is that you really understand what it's telling you. Again, it seems obvious, but if you do these things routinely and you're following an SOP and the protocols are the same as ones before, that's quite normal, then you might lose sight of, well, what exactly is this telling me? So I would recommend have a think about that. Next time you're writing a protocol, have a think about every little detail and what that particular detail is telling you. So I thought I would ask you this and see what sort of situation that you have in terms of setting acceptance criteria. So I've given you a list here to have a little think about. So how would you decide what acceptance criteria to set? Would it be, oh, well, I've done it this way before, so I've done it the same as in previous protocols. Maybe you have a defined guidance document from a respected authority. That's not that often. That can be a bit problematic. ICHQ2 doesn't give us any values, does it? It's a bit of a pain. But if you have guidance documents that are focused on a particular type of method or a particular type of sample, then sometimes you will get values, and I'll show you some of those later. But one that comes to mind is the bioanalytical guidance from FDA and EMA. It's focused on clinical trial samples. It's focused on those biological samples. So you will get acceptance criteria in that. Some of you, it might be an in-house SOP. So you might in your SOP have, these are the criteria we normally set. And some might be just, we went in a course. So we learned about it that way. And if you have got other as your answer, I just thought, well, you might want to share what it is you do. So you can use the chat if you wish to think about what you want to share. So we're doing quite well. The numbers are coming up there. We've just got 2 more, I think. Very good. So let's have a look and publish these results, see what we've got. Well, we've got sort of equal numbers between those 3. So either using the same approach as you used before. Sometimes it depends, as I said, what you're validating. You might have a guidance document and sometimes an SOP. So what I'll try and show you in this webinar is why that's a reasonable approach. So I'm going to try and give you a better understanding of where it comes from, but ultimately that is a reasonable thing to do, and that's what we're going to aim to show you exactly why that is. Okay, let's have a look at what we're going to cover. Well, I'm going to focus on accuracy and precision, because they tend to be the hardest ones. So I'm going to focus basically on quantitative methods. And the thing about a quantitative method that's really important to get in your head before you start is that the result you generate is an estimate of the true value. Now, why do I focus on that so much? As analysts, you're all thinking, yeah, that's obvious, that's fine. But sometimes the people we give the results to don't realize that. So we have a C of A and we've put maybe an assay to 2 decimal places, and they see that and they think, oh, that looks really good. And we know, yeah, well, it's our best estimate, but it's not necessarily accurate to those 2 decimal places. Or you could have a situation where we know, and we'll talk about why now in analytical error, that you could have a result for a pure substance that says it's 100.1% pure. And you're thinking, that doesn't work. But for the reasons we'll discuss, that could be the case. So it's an estimate of your true value. And what we're interested in is how good is that estimate. So 2 things that are important here. How representative is it of the actual value? And how much does this result vary every time we follow this method? Because we're not going to use the method once. So when we're validating, we're trying to think about, in routine use, we'll use this method every time we use it. Is there any issue there? So there are 2 things that we want to look at. Now, in terms of, well, what influences both of these, it's analytical error. And it depends on your background how familiar you are with analytical error. I find a lot of analysts who work in labs don't necessarily come through an analytical chemistry background, and they might not be as aware. But if you have come from more traditional, you've done chemistry, you've done analytical chemistry, this is probably a very familiar concept. So what we're talking about of error in an analytical method is not a mistake. So that's the key thing we have to make clear. It's not human error. Obviously, human error is really important in our industry. We're always trying to find ways to reduce it, especially in labs. It can give us a lot of downtime, a lot of OOSs. It's a problem. But what we're talking about in acceptance criteria is analytical error. So that's where we're focusing on. So a bit of a definition for you here from UPAC, and it's talking about how close you are to the true value. So it's pretty easy. How far away this result of this individual measurement is from the actual value. And we don't know what the actual value is, rarely. So what we try to do in validation is use some conventional true value. And that's what this bit's about. And typically that's something like a reference standard. So something that we can assume we have a true value for. Now when it comes to these error sources and these errors that we find in methods, it is inherent in everything that we do. And we have 2 different types. We have random errors and we have systematic errors. And it's really good to have a little look at this and refresh your knowledge if this is things you've come across before, and see how they relate to acceptance criteria. So let's have a little look then at some definitions of these. This one again I've taken from UPAC. These definitions are a little bit wordy. There's quite a lot of tricky sentences. But the key difference, here you're talking about a measurement, an individual measurement, and then how much it varies from the mean of, as it says here, an infinite number of measurements. So you do it over and over again, and it's how much that individual varies from that mean. Whereas a systematic error is actually based on the mean. So you get the mean of lots and lots and lots of measurements, and how far away are they from the true value when you get the mean of them all. So slightly different way of looking at it. A more simple version, well, the random errors, the more times you do it, the higher the number of replicates, the better the estimate is of the mean. So that's straightforward statistics. That's why we do replicates. That's one of our challenges in analytical chemistry, is trying to figure out, well, what number of replicates should we do? Because it takes a lot of time to run replicates. The systematic error is something that influences every single measurement that's done. So that means it doesn't matter how many times you do it, it's still there. So it's slightly different in terms of where it affects us. So let's look at random errors first of all. These are caused by lots of little uncontrollable variables. So they're noise, background basically. They're very small, some of them. They would be very, very difficult to identify how much contribution they actually give us on their own. But when they all accumulate together, we can look at the total. And it's much easier sometimes to look at that total. So we do lots of replicates to do that. Now, because it's like noise, We have some that are above the mean, some that are below the mean, and we generally get a normal distribution for most physicochemical types of methods we run in labs. Maybe not all, we have to be careful about that, but most. And that allows us to use statistics. So we can use the mean, and we can use in particular the standard deviation. Because the standard deviation is a way of measuring this bell-shaped curve that we get from a normal distribution and putting a number on spread. So when you do your acceptance criteria for your protocol, which I think most of you are quite familiar in, you put an RSD or a CV, which is a measure of spread. And that's coming from this assumption that we have a normal distribution. So it's very convenient. So let's look at a few examples. It's usually easier to really understand these ideas if you think about examples. Here I'm showing you this analyst is filling up to the mark in this 250 volumetric flask. It's not that the analyst will make a mistake, but every single time they do that, it will be slightly different. It's really obvious if you ever use very small volumetric flasks. I know in the past I've used very small ones, maybe 4 mils. 5 is probably as low as we like to go, but one drop can make quite a bit of difference whenever you're topping it up to the line. So you can really see it in action there. But it does mean that through no mistake, there's just some variability. It's small. That's why we use glassware that is designed in this way, but it's there. Another one, still volumetric measurement, pipette, exactly the same idea. We have filled to a line, we have that meniscus, and it's not going to be exactly the same every time. I think this one might be more obvious if you're used to using automated pipettes, because you maybe have measured this variation. It's not unusual to calibrate these before use. How do you calibrate it? You do a fill-in weigh. So you take a certain amount into this tip and dispense it onto a balance, and you look at the spread. And you're not expecting every single time you do it to be identical, so that is the random error already that you're measuring if you do that sort of fill-in weigh experiment. Weighing also has got some variation. For those of you who have calibrated a balance, we very often do a repeatability check. So we take a check weight, we put it on, we measure it, take it off, measure it again 10 times, and we look at the spread. It's very small on a balance. That's why they're so expensive. That's why they're designed to be useful in an analytical environment, but it's still there. So it's one of these small background noise type contributions. And probably the one that if you use chromatography you're very familiar with is the variation from an auto-injector, but by the time you measure it, it's gone through a detector and also an integrator. So it's a combination of different sources of error. But ultimately, every single injection is slightly different in terms of the measurement it gives. And the reason I say you're probably familiar with it is that we use this in system suitability. We don't get 0. We know that there is some variability there, but as long as we consider it to be under control, we're happy. So this is a lovely example of how bad am I going to let it be? And that's what your system suitability acceptance criteria is all about. Another one, integration. Well, I mentioned that the injector is really a combination of this, isn't it? It's a combination of everything that happens to give you the measurement, and the measurement's taken from the peak. But you know that the little start and the end for these little peaks is variable. So if you do multiple injections, you will have some variation there. Okay, what about you? Can you think of anything else? So I'm giving you a bit of a challenge. See if anyone can think of any other possible examples of error sources in analytical method from random error. So feel free to type into the chat box. We'll see how brave you are. Oh, we've got some typing. Fantastic. Okay, so we've got, plasma extraction, lovely one. And I think if you're doing plasma extraction, that's coming to mind straight away because that's what you do. But for all of you that do sample prep, if you have any sort of sample prep, if it's some other type of extraction, if you do some sonication, if you do other things like that, then yes, this is a big source of random error. If you do liquid-liquid extractions, solid phase extractions, then definitely. And sometimes they can be quite high, the amount of error in those more complex extractions. The next one we've got temperature. Yes, so it depends on the fluctuation, whether it's maybe in an incubator or whether it's part of your sample prep or whether it's your ambient, what level and what sort of error that produces, but that's a great one. Oh, I like that, a change in colour and titration, yeah. because it's a judgment, isn't it? If you are doing a colour titration, the analyst is the one who has to decide when it's changed colour. So it's not going to be identical every time. But they do tend to be really good, don't they, in terms of precision and accuracy titrations. That's super. Thank you very much. They're great. Oh, we've got one more before I rush on. I can see somebody else typing a little bit. I have faith. I like that. So it's very good. Okay, systematic errors. What about these ones? So these are slightly different. Random is all about variability. You do it lots of times. You get a slightly different answer. Systematic errors have a cause. They have a definite value. And they have a magnitude that's always positive or negative, and they give us what we call a bias in the measurement technique. Now, systematic errors can be a bit more complicated than that. It's hard to cover this completely in a short webinar like today, but sometimes the systematic error can be variable. So, you have a double whammy. An example of that might be something like a kit where you prepare a sample on that kit, and every time you buy it, it's slightly different. So there'll be a random error associated with those different batches, say, of material. So it's not always clear-cut, is my point. So let's have a look at some simple examples. Keep it straightforward, I think, for the examples. Volumetric glassware. So we looked at this in terms of filling to the mark, but it also gives us a systematic error. And one of the systematic errors is to do with the temperature. So whenever you calibrate your glassware, it's usually calibrated at 20 degrees, or if you are in more tropical climates, maybe 28 degrees. And when you're actually using it, your lab may not be controlled at that temperature, so it will be a slightly different volume. I say slightly, we're talking about small amounts here. The reason that we buy expensive volumetric glassware is it's very much under control, but it might accumulate with other systematic errors in the same direction, and then you start to see it. It's why your method is not perfect. Other examples here could be the tolerance of that glassware. So I talked about the temperature, but there is also the fact that when we have this little 250ml flask here, we're not claiming it's exactly 250.00. We're allowing it to have a tolerance, and typically in this flask it's about 0.12 of a mil. So every time then that you use the 250ml flask, it could be somewhere plus or minus that 0.12. So there's a slight systematic error. And this is a nice example of one that's not going to stay constant, because every flask in your lab might be slightly different. And you'll use different ones for each analysis, so it turns into a bit more of a random error, but it's a systematic error at the start. Tricky? Yeah, it's a little bit tricky. But you can see that there is that little systematic difference. Same with an automated pipette. You have a tolerance. When we do that fill and weigh experiment, I talked about looking at the RSD for the repeatability. The other thing you will look at is just the values you got, maybe the range, and they all have to be within a predefined range. So you're saying it doesn't necessarily have to be exactly the value, but within a tolerance. So there's your systematic error. Auto-injectors. We looked at injection and random error. We look at it here. The accuracy of the injection volume. So it may not be exactly 5 microliters, it might be 4.99. And it depends what you're doing, whether that matters or not. Sometimes it doesn't matter, because you're always injecting the same amount. So as long as the random error is under control, you're good. But if you did try and do sophisticated things by injecting different amounts of standards to create calibration curves, then you would be very reliant on the accuracy of that injection volume. And you'd want to be absolutely sure that the equipment and the system was able to do it for you. Mass measurement, another one that I think if you've ever calibrated a balance, you put on those little check weights to check what comes up on the display, and it doesn't have to be exactly the weighing, it can be within a certain range. So a small systematic error is allowed. This one is a little bit different because the others are more inherent in those measurement systems, very much under control, very low. This one might be something that you actually are involved with choosing. So you can see here I have two options for this rider peak on this large chromatographic peak, and we can either skim this small peak, or we could draw perpendicular down to the baseline and integrate it that way. And just out of interest, I wonder, would you have a preference in that in terms of which you think would be correct? Which one would you decide to do? Because some of us have very clear opinions on what we think is the most suitable thing to do there. If you're not chromatographers, I apologize. This is just a little case study just to have a little look. Okay, we're getting some good responses in here. Mostly A so far. A is winning. Oh, we've got some more A, yeah. I think the answer to this one, from your own perspective, it really depends on what you're used to and what sort of chromatography you're used to looking at, what you think is the most appropriate one here. Okay, so most people have answered, so we'll publish what we've got so far. So most people A, a little bit B, and the third one C, it depends. I like it depends because I'm a consultant, and if you've ever asked me questions, it's very often the answer. And I think it does here. Now, why you would choose A is maybe because in your environment, that's always what you would do, and that's fine. And the same goes for B. In the environment you're looking in, that's always the thing you're supposed to do. But the reason I say it depends is because, well, it depends what you're trying to do here. Say we were only interested in peak A, or sorry, in the big peak, and not in the small peak. Well, if this one doesn't matter, then probably A is the best. If we're only interested in the small peak, then that probably underestimates it. And this probably overestimates it. So we've got systematic error that's negative in direction here and it's positive in direction here. So you need to decide, well, which of those is the most useful to me? Would this maybe be an impurity analysis? Because if it was, I might be quite happy to always overestimate that impurity, especially if it's in a drug, because then you can say to the regulator, well, the patient is always protected because if anything, I'm overestimating the impurity, not under. So you can see why I would go for it depends, but I think that you're all correct in the answer because it's your own experience of the sorts of chromatography and the sorts of sample that you run determines your answer in that one. Any other ones? So can you think of any systematic errors? There's some quite big ones that I haven't mentioned. So again, let's have a look at the chat and see if you have any you want to put in. Any thoughts on this one? We're struggling a bit more with that one, I think. Okay, well, how about I help you out? What about a reference standard? So if you characterize a reference standard and you assign a purity value to it, well then, if you don't have the right purity value, it will always have that systematic error of whatever you've assigned. That's why they're so expensive. Okay, so that's why we put so much effort into characterizing these things. Any other thoughts? So some of you were doing extractions. Yeah. So you have both really. We've got the random error. You were quite correct when you talked about it previously. But you also have a systematic error because if you have an extraction of something complex, you may not always be able to extract it out. Okay, so we had some typing. I think changed. Detectors. That's a nice one. Yes. So a detector could very easily give you a systematic error, and it depends on the detection technique and how it's measuring it, and it could just be a resolution issue with a spectroscopy instrument, and it could be with where it's set, that type of thing. But yeah, definitely. And I think we have one more typing before I move on. Yeah, humidity. Okay, so you've got this change, and temperature came up in the previous one. I think humidity and temperature do give you those sorts of possibilities. So you could find that in your lab you have slightly different conditions. I think humidity is a good one there because it's much harder to control. So whenever I first started working in labs, temperature was not controlled very well. It was very hot during the day, it was very cold during the night, and you would have different sorts of experiences in summer and winter. But nowadays labs are temperature controlled quite well, but humidity is much more difficult. So I agree that's a really good one. And stability of reference standards, yes. So as it goes off, you are losing some of the potency perhaps, and you're assigning the wrong value for it. So you have a bias there. That's really good. Excellent. Thank you. Okay, so we're talking then about these errors. Ultimately, the two things that we had to ask earlier, how representative, how much variation, are systematic error and random error. And ultimately then, how do we look at those in our validation? We look at accuracy and we look at precision. Now, I'm using accuracy because typically I work in pharma, but if you're not from a pharma background, you might know it better as Trueness, and it's a bit of an involved conversation for a short webinar. But if you come on a course, I can talk to you about it a lot more. So this inherent error that we've been talking about, it is there, but I'm not saying it's a big deal that you have to worry about. But what it does explain is why your method is not perfect. We minimize it. So we use analytical approaches. We use balances that are designed to work in an analytical lab. We use volumetric glassware. We decide what class of volumetric glassware we're going to use depending on the error we expect. If we're working with low amounts of error, we use class A. But if we know that inherently what we're dealing with is much higher error, then class A glassware may not be worth it because it's more expensive. So in a micro lab, you're much more likely to use class B. A calibration of your instruments, well, we put a lot of effort into that, and that's all about controlling the error of those systems and those reference standards. So characterizing those reference standards, we put a lot of effort into that to make sure that we have the right value. And we also control these errors. So all of the things in this previous slide about minimizing but also in controlling it are really your quality system in a laboratory, how you control the data quality at the end. So we have well-written methods that are really clear about what the analyst has to do, combined with, you might call a method an SOP, or you might have other SOPs that support the method, how you do things, how you set up the HPLC, how you manage your samples and so on. And then it's the people, isn't it? So we train people really well. We make sure they're competent to do all these tasks and to work within inherent error and not introduce human error. So that's how we make sure it's as low as it can be and under control. Now, before I move on to looking at actual acceptance criteria, I just want to talk a little bit more about the concept of error. So far, I've been talking about inherent error. There comes a time when you might like to say, but how much is it for this method? And that's where we come into measurement uncertainty. So this is basically allowing you to put a value on your measurement of how uncertain you are about the value you quote. And this is a little definition from ISO, and it's saying it's a parameter associated with the result of your measurement. It characterizes the dispersion of values. It's a range. So basically, here's my best estimate, but it could be between here and here, and you've got a range. Okay, so that's what we're looking at. So I just wondered, in terms of your own experience, have you encountered this term? Because I find in pharma it's not as common as in terms of understanding it. So I think in literature you're seeing it more and more, which is great because it's a really important concept, and it's something, a way of trying to put a value on something that you're talking about in more vague terms when you talk about error. What you'll find outside of pharma in ISO labs is we actually do put numbers on it. And the reason for that is very interesting because it really goes back to the fact that you have an analytical lab producing results, and that's what they're getting paid for. So the customer really needs to know, well, what sort of uncertainty is in that result. So that's where a lot of this came from. It was about customer focus and about trying to give people some idea of how they could interpret results. So we've got predominantly yes, which is great news. If you do want to know more about it, a couple of references here. This bottom one is the ISO guide, which is quite complicated. This is a lovely interpretation of the ISO guide for analytics. So I definitely recommend this document from Eurochem. Okay, so we've looked at sources of analytical error. The other little thing we need to consider in acceptance criteria is magnitude. Because generally, if you have those errors that we've looked at, those examples, then you have a situation where, the amount of error we accept is going to be higher for low levels. So therefore there is that low level methods like an impurity, we tend to have bigger ranges. We're going to allow more error than we allow for, say, an assay. And it's not because we're more relaxed about those and we don't mind so much or it doesn't matter. It's because that's what we will find happens. And I'll show you an example of it here. You can see in our chromatography, if we are defining the start and the end of these peaks, then the small differences in this larger peak that we might make from injection to injection, we looked at this earlier as a random error, are going to not really have an awful lot of effect on this very, very big peak. But the same amount of change at the start and end of these little small peaks from our impurities will have a much greater proportion of the peak and therefore much bigger error. So that's just something that we accept. And you'll find a lot of acceptance criteria are really based on that. So you have two real things here, the amount of the analyte in your particular sample you're measuring and those sources of errors that we looked at earlier. So another question for you. So do you think about this? If you're setting acceptance criteria, is this something that you would really think about? It's okay if you don't. So, you'd be quite normal if you didn't, but let's have a look and see. So yes is winning. Oh, no's taken over. So we've got, yeah. Normally what people do is maybe in method development, if you are the method developer and then you're doing the validation, you might have had a look at some of the errors, and I would encourage that. I think that's a really good idea, because you might know you have a tricky extraction, so you might do a lot of experiments on it, so you would have a very good idea of how much error there is. Okay, I think I'll publish that. So we've got a pretty good split, sort of even enough that yes and no. So that's really promising. And this goes back to your question earlier. I won't ask you it again. But we said that it was these three here, A, B, and C, were kind of what you did in terms of setting acceptance criteria. And you can look at generics, and the reason that we can look at previous ones and we can look at generally what's good is because all of those sources are quite similar in similar types of methods. So what I would say is that generally you can set some defaults for your particular types of samples and methods, but what might happen is occasionally a method is harder to develop and you might have more sources of error, and in that case you might want to allow yourself a little bit more flexibility and you might adjust your acceptance criteria slightly. But these default ones in your SOP, in previous protocols, maybe from guidance, will usually work very well. So these are just some numbers for you, typical values for accuracy. Now I've taken these, you can see at the bottom here, this AOAC. This is the Association of Official Analytical Chemists. It's just one group that specialise in this area. They wrote some guidance and you can see it's specific to a certain type of sample. So these are for dietary supplements and botanicals. So they're saying that the amount of recovery it's expressed as here. So we're saying that it has to be within 2% in the low end, 1% in the high end. Depends on how much of your material, your analyte, is in the sample. So if you have a pure sample, they're allowing a bias in the negative direction of 2% and in the positive direction of 1%. But as you have less and less of your material in the sample, you go down here further and further, where we've maybe 1%, we're now given a much greater range. And when we get down to ppm and ppb, much greater ranges. So this is where we are with setting acceptance criteria. We're kind of guessing. We're thinking about, well, what's typical for this sort of method? What have we seen before? And we're judging it against what's gone before. It's very empirical, isn't it? And that is where acceptance criteria come from to answer our original question. And that's why it feels a bit vague sometimes. And I sympathise if it feels a bit vague, because it does. In this case, you can see that they're not even. So we've got 98 to 101, it's 2% in one direction, 1 the other. You don't have to do this. I suspect the reason that it's done this way here is that they're expecting more issues with extraction because these are botanicals, and thinking the systematic error is more likely to be in that direction and you're allowing a little bit more, but you're not expecting so much in the upper direction. So it's probably that reasoning. In pharma, typically we have something like this for our two sort of ICHQ2 type situations. So assays, maybe 98 to 102, impurities, maybe 80 to 120. That sort of value is quite typical. And they work quite well. I'd be very wary though with this one, the assay. If you're working on a drug's product, that's usually fine. Because in most markets you have sort of 95 to 105 specification limit. Other countries might be 90 to 110. You're always targeting to make it at 100. So even if you have a systematic error in the method, you'll still get a good result in terms of whether it's passed or failed. Your risk is that when it's close to the specification limits, it's OOT, then it might actually register as an OOS result if it's on that basis. So if you have a negative bias at this end or a positive at this end. Where this wouldn't work is a drug substance. So you've maybe a small molecule type of drug substance, and your specification limit for that would be typically 99 to 101 or 99.5 to 100.5. So that's not going to work at all, is it? Because if you allow a 2% bias, every single result you do with that method will be 2% out, and every single batch you ever test will probably fail. So you need to be careful sometimes in making these distinctions and making sure that you don't just go with a generic value and think, oh, well, that'll work for everything. Because the reality is, you have to think about it. Precision, we have a similar situation. You can see that this time we're talking about an RSD, we're talking about the spread of our data, our normal distribution, and the typical values go up, and we have more and more error, basically, as we go to lower and lower concentrations. So pure substance maybe somewhere around 1%, 1 or 2%, depends what sort of sample you're dealing with. As you go down to ppm, ppb, you can see sort of 6, 15 sort of levels. In this case, it's again just from what we've seen. It's from what's typical. This particular guidance, these numbers do come from a little equation that you can put on what's typically seen, but it's completely empirical. It's just looking at what's normal and then predicting what you'll get based on that. But what it doesn't really take into account is your sources of error. So it's not all about how much is in the sample. So I think as a generic approach, how much is in the sample is a good starting point, but what you might want to give yourself is a little bit of flexibility. So if you have something very new comes into your laboratory and you know, well, there's a lot of error because it's quite difficult, if it's a complex sample preparation, then you need to give yourself a little bit of room there and maybe do some experiments before you set the validation protocol, because that's the key issue here for this accuracy and precision, is that very often we don't have any experiments prior to doing the validation because it's a lot of work. So we're trying to say, well, what's normal? We set that as an acceptance criteria without really knowing whether it will pass or fail, but we're hoping that it's typical. Okay, so that's our acceptance criteria for precision. Somewhere around 2% is probably quite typical, around 10 to 20% for impurities. And that, remember, is just an expression of the standard deviation. And they are just coming from what we typically see. So we'd consider something less than 1% to be a very precise method. So our summary then, what have we covered? Well, the first one is that the acceptance criteria are about a minimum standard. So the way I've put it, and I know it's a little bit rough, but how bad will I allow my method to be isn't necessarily a bad way for you to think. Second point, the result that we generate following the method is an estimate of the true value. That's a good thing to consider when you're thinking about data and results. The reliability of this estimate relates to how representative the result is of the actual value and also how much variability there is. Okay, so those are our two inherent errors. So we have systematic and random errors in our measurements. And finally, just to be aware, it's not all about the source of the error, it's also to do with the sample itself and the amount of the material. So generally, analytical error has a greater effect when the amount of material is low.